try to comment. Yeah, so this is just a simple board. And what's happening is these are the pegs that they have arranged. And they're just dropping balls randomly. So these balls are dropping in. And we are trying to see where do they accumulate at the end. And these are the bars that we have at the end. And now we are just letting them fall down, okay? And it's really not that complex as well, because if you see a ball is, let's say here, there's a half a chance that it could go to the right or it could go to its left, right? And that is how the probabilities work up. And you'll get something like this. Yeah. And this does look like, you know, that you have what's happening. Okay, I think maybe they're showing it again just to see what's going to happen. And yeah, this is what you will get. More of the mass of the distribution is located near the center, and at the end, it just tails off on the both sides. So you see what's happening here. If let's say a ball is coming from here, there's an equal chance that it could go either in this space or in this space. And once a ball is here in this space, there is again equal chance that it could either go here or it could go here, right? So what we are doing is we are dropping balls from randomly, we are dropping them every time from the middle of the board, and they distribute here randomly. And we know that there is a randomness, but still we're trying to see if there is some order in that randomness. And that is what's happening here, because of the probabilities, you know, half, you know that there is a more chance always for a ball to lie in the center than on the end here, because it has to always go from here to here to here, so as to be able to drop down here, right? But if you start from here and once you go there, or let's say if you start here and once you go to your left, there is more chance that the ball will still be, you know, in the center. So it falls off here and it creates a higher bar in the center. And this is actually known as Galton board. So yeah, that's all I wanted to show you guys. So today we'll learn about, you know, various other distributions. And again, we know that, you know, this normal distribution, which was our favorite, at least up until now, is of no use to us anymore. Because what we are trying to care about are the losses that the company might incur. And we know that they do not follow, you know, a symmetric distribution, or we know for a fact that they are not only symmetric, but that a probability that a claim of a very high amount will occur is much, much smaller than the chance that a claim amount of a lower amount will be incurred. So you get a right-tailed distribution here. All right. And I think today let us start with some very basic distribution. Yeah. So today we will start off with a very basic distribution, continuous distribution, in fact, which goes by the name of exponential distribution. Can anyone tell me what do they know about exponential distribution? Anything that comes to their mind when they hear the word exponential, leave apart its distribution.
It is either continuously increasing or decreasing.
Exponential is either continuously increasing or decreasing. Okay, what does that mean exactly, Mihir? So do you mean when you're saying that, you know, it is either continuously, okay, wait, I'm not sharing my screen, right? Let me share it. All right. Yeah. So whenever we are talking about exponential, what comes to Mihir's mind is Rather, it is decreasing. So it could decrease in any way, right? You just said that it continuously decreases. So it could either be this A line, this B line, or this C line. And when we're talking about continuously increasing, again, we have three different types of increases that we can see depending on the slope, right? What about others? Why is everyone so quiet today? Anyone? So Mihir, is this what you meant?
Actually, C part is somewhat like exponential increasing function in the second graph.
In the second graph, you see this corresponds to exponential.
Part,
okay,
yes.
And in the first part? Anyone else would like to try?
I think the A part in the first graph.
You think the A part. Okay, what about others? I think each one of you have already studied CS1. Am I correct in saying so? Or do we have exceptions? Come on, I guess I could have a yes from everyone. Or no, if we have an exception. Hello? Should I call you all by names? I guess Prajakta has tried something. Prajakta is saying yes. Thank you, Prajakta. Okay, if you all can speak out, it's okay. You know, if there is a noise in the background, I am perfectly fine with it. And I don't think there is any issue to any other person here as well, as long as we can hear you clearly. And that is all that matters. Because I think learning happens not only in one direction, but it has to be, you know, simultaneously with interaction so that we can actually know, you know, where do we need to start from. Okay, so that's cool. So this is what came to your mind when I said the word exponential. And now if I talk about exponential distribution, what exactly comes to your mind? So now I'm talking about exponential distribution. Anyone? It's CDF, it's PDF, it's mean, it's variance, it's boundaries if there are any. What is it that comes to your mind first? Or what does it say? Or like when do we use exponential distribution? Or maybe is it too much of a gap between CS1 exam and CS2 classes? Okay, I think I got a nice yes from everyone. Okay, I want you all to unmute yourself and please speak up. So what comes to your mind when I talk about exponential distribution?
I think it's related to some rate between two successes.
Yes.
Time interval between two events.
That is correct, Anvaya. Yes. And what do other people think? Do you all agree with what these guys just said? Or do you have any other interpretation, which might as well be correct as well? Yes, Vanshika?
Yeah, time interval between two.
Time interval between two events. Yep. And I guess we have something from Prajakta. I agree. Okay, thank you very much, Prajakta. Yeah, so I guess that is all we need to know about exponential distribution. Is that so? No, right? So let us start with some basics. exponential distribution wasn't derived, just as other distributions are. It was kind of a byproduct of something else. So I guess you all know about Poisson process. So you all must have studied this distribution, I guess. Some people call it Poisson, some people call it Poisson, but it's actually Poisson. And even I forget the pronunciation sometimes, but I try to be true to it. But yeah, so we have something known as Poisson, and on the other hand, we have something known as exponential. Does anyone know what Poisson does?
It measures.
Defined as
Oh, I couldn't hear any of you.
The rate of an event happening, like number of
rate of-
calls per day or something like that.
Exactly, Ishai. And where do you want to add something to it?
Ma'am, it is the number of events that occur up to time t, like, up to certain time, right?
Up
from
to
the
certain
beginning.
time? Okay. Or it could also be, within a single unit of time, right? So
Yeah.
the very famous example that we have in statistics always is about, the number of cars that pass any toll gate within an hour. So the stipulated time that we're looking at here, the one unit of time for us is an hour. So what we're looking at is the number of cars passing the toll gate. And when I'm talking about exponential, the analogous event to this within exponential could be the number of hours between the arrival of each car. So this would be the number of hours between the arrival of cars, right? And as rightly said by all of you, in Poisson, what we are measuring is events per single unit time. So we do measure events. We do measure how many number of events have occurred when we have a defined event, which in this case is the passing of cars, right? So what we are measuring here is events per single unit of time. So our unit time here is 1 hour. See, I forgot to write. So we have number of cars passing the toll gate in an hour. Okay? Yeah. And when I'm talking about exponential, again, this is just the time. So the time here is again hours. So here time, we don't have a unit of time. I mean, we do have unit something like hours, but we can again convert it to minutes and it would still be another unit. So the time is being measured in hours here. And this is just time per single event. Is this clear to everyone? So again, we know that, Poisson is something which is a discrete distribution, right? And exponential is something which is a continuous distribution. But we know that they both, in a way, act as if they're inverse of each other. So how could it be the case that one is discrete and other is continuous? Does anyone have the answer to this? Has anyone ever thought about this?
Events are discrete and time is continuous.
Yes, right. So we know that the time is continuous. So when we are trying to measure time, we know that it changes within seconds and even within nanoseconds. So we know that it is something which can be measured on a continuous basis. And when we're talking about events, we know that there cannot be, half a car passing the toll gate. I mean, in literally, it can be, the fact that only the half of car has passed the toll gate, but bear with me, we don't take that into consideration. So what do we define a car passing is that the whole body of the car has passed through the toll gate, right? And that is our event. So if that is the event, we know that half a car passing is not an event at all. So there can either be an event or no event. There cannot be something in between. And that is why we measure it in discrete times. So there can be either one event, two events, three events within an hour. So one car passed, two car passed, or three cars passed, or no car has passed within an hour from the toll gate that we have taken into consideration for the event that we have described here. Okay, so again, now when we are talking about these distributions, this is why we need these distributions. Okay, now let us see how they look like. So I guess you all must have guessed, because we have Poisson, it would look something like, so we will have some chunks here, right? We'll have bars of graphs, something happening. So please mind my straight lines. These aren't straight, I know, but yeah. And here I'll draw the exponential. So again, whenever I'm talking about a discrete distribution, so let us say the number of events we plot here can be 1, 2, 3, 4, 5, 6. So these are the number of cars that are passing the toll gate, and this could just be the chance. Okay, and so on. So this is how okay, let me ask this question. What is this? What is this? What is this graph that I have just drawn here?
Bar plot.
Anyone? It's a bar plot, yes. Anything else? Okay, maybe let me give you guys a hint. What is the full form of PMF?
Probability mass function.
Yeah. What is the full form of the PDF? Sorry, what is the full form of the PMF?
Probability mass function.
Exactly right, probability mass function. So whenever I'm looking at a discrete distribution, remember we have a probability mass function. And let's say on the other hand, if I'm looking at the exponential distribution, which will be continuous, and again, I think there is a nice story, why is it shaped in such a manner? Like, why do exponential decay looks like this and not like this or like that or like this? Why is it decaying drastically, So maybe if you all are interested, we might do that as well. So let me just, do the housekeeping work. Yeah, so we have this stuff here. And again, these are the hours that I have plotted, and these are the number of events here. Okay. So here I know that this represents something which I write as f of x, which will essentially be the PDF here, right? So if I'm defining this variable that I'm plotting on the x-axis here as small x, which is the time here, so this will just be f of x, which is just a function of x. Because for each x, I'm getting some value on the y, not randomly, but I'm substituting this x value in the PDF, which is my function, and then my output is this thing. So this is what I get on the y-axis, right? And so these are the number of events that you have. And here that represent, yeah, again. So this is, again, some sort of difference that you now see here. So remember, here what we are measuring is the number of cars that are passing from the toll gate per hour. And here it would be the time until the next car passes the toll gate, right? So the number of hours until the next car will pass the toll gate. So again, this is just the skeleton of this distribution. Now, if we have to get into the nitty-gritties of it, we know that we define any distribution with the parameters that it has, right? Does anyone know what are the parameters of Poisson distribution?
Lambda.
I'm sorry, lambda, right? I'm sorry, Prajakta, I just saw your answer. Welcome. So, okay, lambda, right? So I have a lambda here. And what does this lambda represent? Anyone?
The rate.
Rate.
The rate, right? The average, right? And this is also the mean of Poisson, right? So this represents the rate. And what is the parameter for our exponential distribution?
Lambda.
Lambda. And what does lambda here represent?
Rate, I think. Same.
Inverse of the rate,
Rate
right?
per time.
Okay, so we have some people saying that it is rate. Some people say inverse of a rate. What about others?
Rate per time.
Rate per time. Anyone who favors some answer? Okay,
Rate,
so
ma'am.
so I would say that both the answers are correct. Only if I look at this lambda here, which I have defined as the rate already, and if I'm again, so we all know, right, that Poisson measures the events and exponential measures the time between those occurrence of the events per unit of time. So if I'm talking about the same events here and there as well, then the lambda that I have here in Poisson is the rate. So I can actually define this exponential distribution using this lambda as well. And if I do that, my lambda here will still be the rate, right? And if I don't do that, and if I use the normal way we define distributions always, so we know that each distribution can be defined by its parameters. So like for normal, we have mu, which is its mean, and sigma, which is its standard deviation. For Poisson, we have this lambda, which is its mean. And for exponential, we can define another parameter, which is mu, which will be its mean. So then this definition of 1 upon rate would hold true. But for now, let us ignore this case. And because we're trying to see the connection between these events, and that is why we say that the lambda here is the same lambda here, and the event of the car passing is the same that we're looking at in both the cases. All right. So to measure the number of events, we have Poisson. To measure the time between passing of each event, which is passing of the car here, is analyzed using exponential distribution. So again, the lambda here, we can define it as just the rate. Okay, that's good. And okay, so whenever I talk about exponential distribution, if I tell you guys, okay, so if I tell you guys that I started my toll gate at 9 a.m. in the morning. So I sat at the toll gate, I opened the gate and, just consider this as a hypothetical example. My duty starts at 9 a.m. So I went to the toll gate at 9 a.m. and I started observing how many cars are passing, okay? And I waited there and I saw that it has been, okay, so let me maybe write it in the next page. So let us start from the start. I started the toll gate at 9 a.m. All right. And now my question is, what is the chance that a single car will pass from the toll gate within 9:01 a.m.? So again, I'll just maybe write it here. What is the probability that a car will pass the toll gate? Anyone would like to guess this probability? It's not possible, right? I mean, there can be no guess at all because we clearly don't have enough information about anything as yet. That's all right. So, okay. So let us assume that there was no car passed until 9:20 a.m. So now the time in my clock is 9:20 a.m. So now I am asking again the same question. At 9:20 a.m., what is the probability that a car passes the toll before 9:21 a.m.? What do you guys think? Yeah, someone had some question to ask?
I was saying that according to the Poisson distribution, the answer for both the cases will be the same, right?
Will be the same. Yeah, exactly. And who was this speaking?
Vanshika.
Okay, thank you. So exactly right. So does anyone have any other answers to this? So I'm not yet convinced with Vanshita's answer. Does anyone else have any other possible explanations for why this could be the same? Memoryless property, exactly, Vaibhav. Thank you very much. So exactly, yeah. So whatever Vanshita said is exactly correct. I was just tricking you guys by saying that I doubted her, but no, I just wanted you all to think a bit. So,
because we are just considering event per unit time. We are not considering the time.
Exactly right. So what we are considering is event per unit of time. But again, if I have only given you guys this much of information, you guys are on the right track when you say memoryless property and that the probability has to be same. But until and unless I give you guys some another information about the cars passing, you can never really say that, these would be the same. So let's say I tell you, that there is a event at 10 o'clock and everyone needs to pass by the toll gate. So I can clearly see a rush at the toll gate around 10 o'clock, right? Sometime before that, 15 minutes before that, right? Because everyone would be hurrying to the event. So there are two basic assumptions that you always need for this and this answer to be the same. Does anyone have any idea of what those two assumptions could be? Anyone has any idea about what these assumptions could be? Something about the events, right? It has to be something about the events. So the very first assumption is that all of my events should occur at a constant rate. There should be nothing else governing the process that I'm observing. Okay, so this will happen. Let me write the assumptions here. So my first assumption is that all of my events should occur at a constant rate. Anyone would like to guess the second assumption? And there are only two. So I'm assuming you all know what IFF means. This means if and only if. So again, my next assumption is that the events should be independent of each other. It shouldn't be the case that, if a red car passes, then there is a higher chance of some another car being passed. It should always be the same. So events should be independent of each other. So these assumptions are very, very important because whenever you see questions like this, I know we have studied memoryless property and we know that, Poisson is the thing that we should use. But again, you should be mindful of the assumptions that these always work the same out in. So you should always remember these assumptions and have them within your toolbox with a small asterisk. Okay, because there is no use of knowing a theory if you don't know when it works well and when it doesn't. So if you use these memoryless property when the events aren't occurring at a constant rate, it will give you some very senseless answer. Or maybe you might try to make sense of it because you inherently believe that this should be the answer. And that is what generally happens with most of the researchers. But then at the end, they realize their flow and it all boils down to nothing. So, yeah, I see something happening in the chat. Okay, I'm memoryless. That's it. Yeah, so this is what's happening. And again, let us say, let me write the heading for this was memoryless property. So memoryless property holds only for exponential distribution. And do you guys know any other distribution which has memoryless property?
Geometric distribution.
Geometric distribution, yes, that is absolutely correct. Any other distribution?
Negative binomial, I guess.
Negative binomial, you guess. Okay. So wait, who is this speaking? Maybe I'll get used to recognizing your voices. What's this one? Anvaya. Okay, yeah, Anvaya. Thank you very much. So yeah, actually, exponential distribution is the only continuous distribution which has this property known as memoryless property. And geometric distribution is one of the discrete distributions which has this property called memoryless. So again, we will learn something about Poisson process, and those are different than Poisson distribution. So if I ask people sometimes, so once they have studied Poisson process, which was a part of CT4 and which we will study in future, they think that, it is a distribution, and so geometric isn't the only discrete distribution which has memoryless property. That's completely false. And we will study the difference between a Poisson process and a Poisson distribution. And there is a whole lot of difference between both of those. So again, I think memoryless property is something that we will again discuss in detail, but I want you all to, get this within your heads once about Poisson and exponential and how do you move around those and how do you answer questions which depend on these graphs. So let me explain you about these graphs in detail, and we'll try to solve some questions which I guess you all must have seen in CT3, but this is very important for us to remember again, not for the CT6 part, but for the CT4 part, yes. So, okay, let me draw the exponential graph once again. So what I'm drawing here is, or maybe I can use the tool here. Yeah, so I have this graph here and I have certain questions about this graph. Okay. So again, remember what we are measuring here. What we are measuring is the number of cars. So the number of cars passing is the event that we are considering, and the unit of time we have is hours. So when I'm talking about 0.5 hours, it actually means 30 minutes. All right. So, okay, my first question is the probability that the next car passes in 10 minutes. Yeah. Does anyone know how will you figure this out? So I'm looking for the probability. Yeah. So I'm looking for the probability that the next car will pass in 10 minutes. Anyone? You cannot clearly say, right? You need me to define what lambda is. So here, my lambda is the parameter. And if I say that my lambda for Poisson is 3. So my lambda here is basically 3. So what do I mean when I say that my lambda is 3? Anyone? Can you put this in words? What exactly do you mean when I'm saying that my lambda is 3? Anyone?
I think it is the average time between the two cars which passes through the toll.
Okay, so in exponential, I am measuring the time. But when I'm talking about lambda here, this is coming from the Poisson distribution. And remember, Poisson is a discrete distribution. So what I'm measuring over there is the number of cars that have passed within an hour time period. So when I say that my lambda is taking the value 3, it means that on an average, 3 cars pass within an hour from the toll gate that I have. Does this make sense to everyone? When I'm saying that my lambda is 3, it means that on an average, 3 cars pass the toll gate within an hour. So now if I have to convert it to the exponential thingy, I know that my average, what will be my average here? So if I'm saying that my lambda is 3, and it means that 3 cars pass in an hour. Okay, so my question now is, how much time on an average a car passes the toll gate in? Anyone? This is a very basic word problem type question, you know, that you get in 5th or 6th standard, I guess. So I know that 3 cars pass in an hour. So on an average, and again, I'm assuming that each of the car passes at a constant rate, and each of these cars passing is independent of any other car passing through the toll gate. So we keep those assumptions always in our mind. And now my question is, how much time on an average it takes for a car, how much time on an average it will take for a car to pass the toll gate? Anyone? Okay, maybe it is not clear in this example. Let us see the actual example, you know. So we see that, you know, there is a beaker which needs to be filled. And if I'm saying that all of this, anyone would like to say something? This project has something in the chart. So saying 3 car passes within a given time frame 1 hour. Yes. So Prajakta, you're correct, but what you are talking about is this. And what we are questioning is how much time on an average it will take for a car to pass the toll gate. I mean, not exactly for a car to go through the toll gate, but for a car to even arrive at the toll gate, right? So
20 minutes.
I couldn't hear you, Vanshita.
20 minutes.
20 minutes, right. That is exactly. And how did you come up with 20 minutes? Can you explain?
The same way we used to do in 5th or 6th standard.
Yeah, right. So can you explain that?
It would be 1 hour by 3, so 60 by 3 would be 20 minutes.
Yeah, and why will it be 1/3?
Because for 3 cars it is 1 hour. So for 1 car it would be X minutes. So then
Right, exactly. Yeah. So we know that if it takes 1 hour for 3 cars to pass, then we know that each 20 minutes, each third of an hour, 1 car has passed. All right. So on an average, we know that each car takes 1/3 of hours to pass. So this is the average that we're looking for in the exponential, right? So if I have to define the mean of my exponential distribution, that is why it is always 1 upon lambda, right? So again, you don't have to memorize this stuff, but you just need to know the intuition and why do we have things the way they are, okay? So again, if I'm writing the mean of this distribution, it will be 1 upon lambda, which is 1 upon 3 in this particular case where I define my lambda as 3, right? So again, coming back to the question that we have, I am posing another question now. We have to figure out the probability that the next car passes in 10 minutes. So if I have to, let's say if I have to plot it here, plot the area here, how will it look like? Does anyone have any idea of how will it look like? So I'm talking about the probability that my next car will pass in 10 minutes. So, okay, let me break this one for you guys and then I can maybe pose another question and you can help me with that question. So when I'm talking about the probability that a car has to pass in 10 minutes, let us see where 10 minutes lie on the x-axis here, where we have the hours, right? So this is 30 minutes. So if I take 1/3 of this, I know that this is where my 10 minutes will lie, right? So if I take this up and above, oops. So if I take this up and above, the area that I get here is the answer to this question. And does this make sense, or does anyone have any doubt with the area that I have just shaded? So what I am saying is that 1 minute, 2 minutes, 3 minutes, 4 minutes, no car has to pass. The event only occurs in 10 minutes. So when I'm saying that the probability that the next car has passed the toll gate within 10 minutes. What it means is that the car could have passed any time, right? Are you guys with me? So previously what I said was 1 minute, 2 minutes, 3 minutes. The car hasn't passed. The car can pass at 4 minutes as well. And there could have been no car which is passing at the 10 minutes. But still, it is a car which has passed within the 10 minutes that we are trying to record. So this is the probability that a car would have passed within the 10 minutes. And does anyone have any idea how do I figure out the area that I have shaded? Anyone?
With the CDF.
Right, with the CDF. Okay, so this is why we need the PDFs and CDFs to be handy formulas, which we can just substitute our values in. So does anyone recall what is the PDF or the CDF of the exponential distribution?
CDF is 1 minus e raised to minus lambda into x.
Yeah, so let us start by, maybe I don't want to write it here. So maybe I'll just write it here with Memoryless. So I have my x here. I have my x, which I'm saying follows exponential with the rate parameter lambda. So remember my mean will be 1 upon lambda, okay? And so we have the CDF as 1 minus e raised to minus lambda x. And again, this is only valid if my x takes a positive value. So we have to remember that we have nothing called as negative time I mean, you can still have negative time if you are in the quantum world, but we aren't. So we take x greater than 0, and the PDF, if we are writing here, will be what? Anyone?
E raised to minus lambda x.
E raised to minus
Lambda into e raised to minus.
Right. It will be lambda into e raised to minus x, where my x is greater than 0. And if you integrate this PDF, so my CDF is what? This is the integration of my PDF with respect to x for all the values of x up until x. Right? And that is how I will get this formula up here. So again, now if I have to figure out my area, which lies below this 10, what I will have to do is just substitute this value of x here, right? Because what CDF measures in a way is the probability that my random variable takes a value which is less than or equal to the x that I'm defining. And that is exactly what we're looking at here. The probability that this takes a value less than this guy. So again, you will have to convert this 10 minutes into hours, which will just be 1/6. And you will get your answer, right? So that's there. And let us try and answer the next question now. So I have another question related to the same thing. Now my question is, what is the probability that the next car will pass after 1 hour? How will this look like on the graph? Anyone?
The part after 1 hour, like, so in the hours part, you would draw a dotted line upwards and the part towards the right.
Yeah, all the part towards the right will come into this. And again, I think I need not reiterate how to calculate this area. What you can do is you can just substitute this 1 in the CDF and subtract the CDF from the 1, because what CDF measures is the part to the left of 1, and we want the part to the right to the 1, and we know that this whole area sums up to 1 because it is a well-defined PDF of an exponential distribution. So the green area would just be 1 minus the CDF at 1. Perfect. So again, next question. This can be a bit trickier one. So now my question is, the probability that a car will pass at exactly 15 minutes. Okay, maybe let me do it 30 minutes. Anyone?
It will be a very, very small probability, almost equal to 0.
Almost equal to 0, right? Why?
Because you're considering a very small part of the continuous line.
Yeah, exactly. So even Anvaya just said that, I guess. So exactly, that is correct. Because we are assuming that this distribution is continuous, and we can ignore all these mathematical facts, okay? Let us see what's happening in real. So I want a car to pass in exactly 15 minutes. It shouldn't be 15.0001 seconds as well. Like that just cannot happen in reality, right? There will be some time passed at least beyond 15 minutes precisely. So the probability that this thing is going to occur, so I can say that my probability that x will take the value for 30 exactly, let me erase it. So the probability that my x will take the value 30 exactly is 0, right? And again, because it's a continuous distribution, we know that this is just not possible. And that is what I say is the curse of continuous distributions, that you can never determine what's going to happen at a precise time. You always have to define an interval within which something will happen. And then you can calculate its probability and all the other stuff. Good. So I think that is all about this Poisson and exponentials relation and how do you answer questions based on this graph. And this is super easy, right? And I don't think you guys should ever forget how to do this stuff, and because this is just very intuitive to me as well, and I guess it is intuitive to you guys as well now at least. So that's good. Again, another question, when I was in my bachelor's, I used to wonder why in normal distribution, so let me go to the next slide. When we're studying normal distribution, I draw a graph like this, all right? And if I have to figure out where is my mean, what will you guys say? Where is the mean of this graph?
At the center, where there is the highest point.
Right? You said at the center, where there is the highest point. So now if I'm drawing my exponential, okay, I'm drawing my exponential PDF here. And where is my mean? It should always be here, right? Why isn't it always up there? Does anyone have any idea about this? Again, this is the PDF. This is also the PDF. And I say that this is the place where I'm observing most points. So this should be my mean. Then why shouldn't this be the mean in my exponential graph? Anyone has any idea of what's going on?
We consider the average.
And what exactly do you mean by we consider the average?
From assuming that the mean point will also shift.
That the mean point will also shift. So you mean
we have extreme values as well. So that is why the mean can be lesser than the highest value.
But we had extreme values here as well, right? I mean, I can just...
No, all the values are positive and exponential. And
yeah.
Might be the reason.
Yeah, that is actually one of the reasons. That is one of the reasons. So in normal, what we see is we have some positive here, some negative here. But that is not always the case. So we know that this is not the reason that we get a graph like that always. But this could be one of the reasons, right? If you look at this graph and if you compare these graphs. So again, not always my mu is 0. My mu could be something like 90 as well, right? In normal distribution. So again, I know that it will go on forever till negative, but we know that a number which is here could also be a positive number. So again, what's going on? Okay, so let us see what happens and why is it that when I'm talking about exponential decay or exponential distribution, I get a graph which is, which decays instantaneously right there. So let us say I define again I'll take again the car and the tool example. So I'm saying that the probability that a car will pass in a minute from the toll gate. So I'm saying the probability that I'll have x in between 0 and 1 is 0.05. So this is the probability that my first car passes in 1 hour. Okay. And this is my answer to it. So again, if I have another question, again, remember, this is the information that I have given to you guys. And now I'm asking you guys a question, which will of course be based on this. And my question is, what is the probability that your first car passes in 2 hours? Anyone has any idea about what should this be? So if I give you the information that my first car has passed, that my first car will pass in a time unit is 0.05, then what is the chance that my first car will pass in 2 hours? Think about it. I'll give you guys some time.
Will it be the square?
Square of
0.05.
and why?
Because the probability of it passing in 1 hour is 0.05 and we want it to pass in, like we are considering 2 hours. So 1 hour and 2 hour, right? So
So
should
you are
we
on the right
multiply
track.
it?
Isha, you are on the right track, but you're not exactly, there, up there. You have taken a divergence somewhere. Think about it. You are thinking in the right direction. I want your car to pass through the toll gate, So can anyone say what does this mean? Oh, the internet went off. इंटरनेट चला गया बोलो तुम इंटरनेट चला गया एक बार देखो क्या हुआ बंद करने को मत बोलना बस अभी रुको शायद आ गया Yeah, I'm sorry, I guess the internet was acting up a bit. So yeah, did you guys get enough time to think about it?
Ma'am, if we try to solve it, can we take like 1 minus e to the power minus lambda as 0.05? Like, because x is 1 here, right? In the first case, if we are taking the CDF.
Just give me a minute. चालू हो गया So yeah, so you said that within 1 hour it's this. Yeah, it makes sense. So what will happen now?
So if we find the lambda, so it is coming as 2.996. So we can consider it as 3, right?
Yeah.
And then similarly, we will find the CDF with x equal to 2 now. So 1 minus e to the power minus 2 lambda.
And what will the answer be?
0.9975.
One minus e2 minus 3 times 2, right? This is what we're looking at.
Yeah.
And what is the answer you said?
0.9975.
Are you sure?
Yeah. That's what I put in my calculator.
Okay. Can anyone verify the answer?
I think it is 0.0975.
No, ma'am, it's 0.9975.
Yeah, it comes out to be 0.9975. But again, my question to you now is, this is not something which is incorrect, I would say. But what exactly does it mean when you put here 0.9975? What exactly this means?
That the first car will pass within 2 hours. The area of the curve
Yeah.
under 2, yeah.
Under, right? So if I'm talking about this, the probability that we have just calculated, it would be all the area under this curve, right?
Yes.
But again, my question is not that a car should just pass within these 2 hours. My question is that the first car should pass in 2 hours. So I could have said 1 hour as well, right? So when I'm talking about such questions, what I actually mean is that the car, not a single car has passed within the first hour. And my first car has to pass in the second hour. Does this make sense?
Yeah.
So, again, when I'm talking about the first, when I write the word first here, that is the difference it makes. So I want my first car to pass in 2 hours. And that is why the answer here would be the probability that no car passes in the first hour, which would be 1 minus 0.05, which is 0.95 times that the car passes within the next hour, which will be 0.05. And you'll get some answer for this, which we don't have to care about. What we care about is the numbers that we have directly from the things that we are considering. Okay, so again, if I put forth the next question, which is similar to this, what is the chance that my first car passes in 3 hours? Again,
0.99 square into 0.05.
so it will be 0.95 square times 0.05. Exactly. Yeah. And you will get so on, as in when you increase the number of hours that you are looking at. So can you see what's happening as in when I'm increasing my x-axis here, which is time? So previously we had 0.95 times 0.05. Then we have 0.95 square times 0.05. And next up we will have 0.95 to the cube times 0.05. So what's happening is 0.95's power is increasing, right? The indexing for 0.95 is increasing by 1 as we pass time by 1 single unit, right? So for each successive hour that goes on, we are increasing the power of 0.95 here. And because you're multiplying the number that we previously had by 0.95 again, which is less than 1, you get something which is a lesser value than the one that you previously had. And that is the reason you get a graph which is exponentially decaying. And that is what you mean when you say that, it is decaying exponentially, because this exponent here increases. And the number that we are indexing is less than 1. And that is the reason it decays. All right. So it could have increased if the number was greater than 1. But here, because we are talking about probabilities, it's decreasing. And again, we have to remember that it will never, 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 ever tail off to 0. It just goes on asymptotically. And we say that it goes on till infinite, right? So I hope that's clear. And we might not require this much of depth about, Poisson and exponential distribution for the first part of our course. But in the next part of our course, it is at most important for us to understand what this questions exactly mean, and we will revise it again maybe that time. And I'm assuming that time you guys will be speaking much more than me. So again, let us come back to the memoryless property that we were talking about. That is what we need here. So where was I talking about memoryless? This right here. Yeah. So I was talking about memoryless property here. There's no space left. Yeah. So again, when I'm talking about memoryless property, let us try to define it, Now that we know what the PDF or the CDF is, let us try and see what happens, in the memoryless property. So can anyone again remind me in words, what exactly does memoryless mean?
The past events do not affect the probability of the future events happening.
Exactly, right? What has happened in the past is of no concern to us. We only see future. We don't care about the past. So let us consider we have two positive numbers, S and T, all right? And now what I want is the probability that my X takes a value greater than S plus T such that my X is greater than S. Shouldn't write probability here. Yeah. So what I want to figure out is the chance that my X random variable will take a value which is higher than S plus T, given that it has taken a value which is greater than or equal to S. So what do you guys think this will be?
It will be probability X is greater than equal to S plus T divided by probability X is greater than equal to S.
Right. So what we are doing is we are using the Bayes theorem here. We have this A event here and we have this B event here. I think we're talking about events, so it has to be probability. So we're talking about A event here and we're talking about the B event here. So what we will have is this A, B upon only B. So what we have here is probability that my X takes a value greater than S plus T and that my X also takes a value greater than S upon the probability that my X takes a value greater than or equal to X. And next will come the step which she just spoke about. So remember, what we had here was probability of A given B, and that will just be my probability of A intersection B upon the probability of B. All right. So that is what we are using. And again, let's go back to this. So I know that if my X is greater than or equal to S, and I'm wondering that these two should be happening simultaneously, right? So let us draw a number line. I know that this is S, and let us say that this is some time t, so this will be S plus t. And again, I'm assuming that these are both positive numbers, so my t cannot be, negative. So again, if I'm already saying that this has to happen and this has to happen, so I know that if my X is greater than or equal to S plus T, for a fact, this will always be greater than S as well, right? So the intersection between these two events will be all the points here. So what I will be left with is just that the probability that my X takes a value greater than S plus T. Okay, maybe let me disable. Yeah. So probability that my X will be greater than S plus T upon the probability that my X will be greater than or equal to S, right? So again, what can I do next? So let us assume that my X here follows exponential distribution with the parameter lambda. So what will happen? Now I have to figure out the probability that my x takes a value greater than or equal to s plus t. And we know the CDF. So what I can do is I can write this as 1 minus the probability that my x takes a value less than or equal to s plus t. And this could be written as 1 minus the probability, some disturbance. So probability that my x takes a value less than or equal to s, right? And this is just the CDF, this is just the CDF. And we know the CDF of exponential is 1 minus e2 minus lambda x. All right. So 1 and 1 would get cancelled. And what will you be left with? Anyone would like to help me with? What will be in the numerator?
E raised to minus lambda s plus t.
Right.
And in the denominator, e raised to minus lambda s.
All right. And this boils down to?
E raised to minus lambda t.
Perfect. This boils down to e raised to minus lambda t, right? So you see that s is nowhere in the answer that you have, right? So s does not matter. And what is this? This can also be written as the probability that x takes a value greater than or equal to t, right? Does this make sense? So now, in a way, what happens is, because of its memorylessness, whatever has happened in the past has no effect on the chance of what's going to happen in the future. So if I have to rewrite this, I can summarize my memoryless property like this. All right. Does this make sense? Anyone has any questions? Okay, so this was all about exponential distribution, which is one of the distributions which you can sometimes use, to describe the losses that will be incurred in terms of claims for an insurance company. So there are certain other parameters which do describe the distribution, as do the parameters of the distribution. So does anyone remember what else describes a distribution other than its PDF, CDF, mean, variance? What is the other thing that we generally know? Have you guys studied about moment generating function?
Yes, ma'am.
Okay, so what do you think it is? What is a moment generating function?
It generates the first moment about 0. I mean, first or second. I mean, it generates the moment about the origin.
I have no idea why is this going on. Okay, does everyone agree to that? Does everyone agree what she just said?
It can generate moments up to the third, fourth, or any power.
Or any power, okay. And how do we define moments? Like, what is a moment?
There is a formula, right? Expected value of e raised to tx.
Yeah. So generally, I define whenever I'm saying I'm talking about the NGF, I only write m of t here. And like I could write anything instead of t, or just not the random variable. I hope you can understand what I'm writing. I don't know why is it creating extra lines. Yeah, so this is the formula, right? And x here is the random variable. So again, we know that if I'm just taking a certain function of the random variable that I'm talking about, even my expectation of e raised to tx will be just some another random variable, right? And we have to remember that I could have taken p, q, r, anything instead of the t that I have. So it's just acting as a dummy variable at the placeholder, right? And so again, when I said that my expectation of e raised to tx is a random variable, I want you all to, say yes if you agree with what I said, or no if you do not agree with what I said. So my statement is that expectation of e raised to tx is a random variable. How many of you think this is a correct statement? And how many of you think it isn't? Come on, you just have to say a yes or a no.
Can you please repeat your question?
Okay, so my question is that the expectation of e raised to tx, basically my function in gf, is a random variable. अच्छा चलो starting से start करते हैं. How do you guys define a random variable? Like what is a random variable? Because every time we are speaking about random variable, does anyone know what is a random variable?
It means it can take different values.
Yeah, that's true. So even if I give you a constant which is unknown, even that can take different values, right? Can a constant take different values? So let's say if I have a constant, if I define, so in the previous case while I was deriving the memoryless property, I wrote some two constants, right, s and t. So what were those? Were those random variables? All right. So those were the random variables. And yeah, so basically these are the random variables. And again, remember this when I'm taking expectation. So let us start from the basics. What I have information about is x. So I know that my x is a random variable, right? And I'm multiplying it with some constant which is t, right? Which is unknown to me yet, but I know it is just some constant. So again, my tx is a random variable, just scaled up by the t here, right?
Yeah.
And now what I'm doing is I'm raising this tx to the power for e. So again, I have just scaled it up a bit, right? So again, my e raised to tx will be some random variable, right? And the next step is I'm taking its expectation. So what happens when I take an expectation of a random variable? Does it stay a random variable or does it not? That is my
Unique
question.
value.
It is a unique value, right? So it will not be a random variable. So remember, the random variable will only be the thing which we are taking expectation of. And once you take its expectation, it is no more a random variable. You have assumed its value in a way, all right? So that was just the motive. And when I was talking about scaling up and scaling down, maybe we can do this at the end. So remind me, any of you, if you want to know, if you want to see the geometric proof of memoryless property, it has to do something with, scaling up and down. And it's really interesting. And we can do that maybe after 4:30, I will be recording it. So if you want to stay, you can stay in the class, or if you have some other work, you can feel free to do so. So let us continue with NGF for now. And again, we will try to see, why do we even need moment generating functions? Like we have mean, we have variance, we have PDF, we have CDF. Why do I need a moment generating function? Does anyone have an answer to that? Okay, so let us see. Yeah, Weber.
Easier to calculate moments.
Easier to calculate? I couldn't hear you. Are you saying easier to calculate? What?
Moments are easier to calculate using MGF.
Could anyone hear what he said?
He's saying moments are easier to calculate using MGF.
Okay, yeah. So moments are easier to calculate using MGF. That is exactly one of the reasons. Correct? And what happens in moments is, so again, I think someone said at the start when I asked about MGF. So we know that, okay, let us start from the start. Whenever we're like, why is it easier to calculate moments using MGF? Okay, so we know that the formula for MGF is expectation of e raised to tx. So let me just write it here. I have expectation of e raised to tx here. And if you guys have formula booklet open in front of you, go to page number 2nd, and using something on page number 2nd, I want you all to say, how can I rewrite this function as? So for those of you who do not have, let me put it in the group. Do you guys have the PDF of this formula booklet?
Yes.
Otherwise, I'll forward it. So I guess I'll forward it anyways. So again, how can I expand this expression which I have here? Anyone would like to help me with this?
1 plus tx the whole square upon 2 factorial plus tx the whole cube upon 3 factorial, so on.
Ex, you said tx, right?
Yes, 1 plus tx.
Yeah, so it will be 1 plus tx plus t
tx
square x square.
Yes.
Exactly, right?
2 factorial.
And
yes. So on plus tx the whole cube upon 3 factorial.
I don't know, my pen stopped working. What's happening here? Yeah, so this is plus till infinity, right? So again, if I have to write this in a condensed manner, how can I rewrite this as? Anyone? So I have to rewrite this in terms of summation. So I'm taking summation from 0 till infinity. Okay. And what will I have here? I have t raised to n, x raised to n upon n factorial, right? This can summarize all that I have. So next up, so remember, you cannot do this always. You cannot always switch between expectation and summation, but as long as you're defining this function on some finite interval, let's say minus a to a, and you assume that a is a number which is greater than 0, you can swap this. So generally for our purposes, that will always be the case, and you need not have to worry when these aren't swappable. But again, so now I'm going to swap this. So I take expectation inside and I pull summation outside. So what will I be left with is something like this. So I'll have summation. So I'll have summation n goes from 0 to infinity, and expectation of x raised to n, t raised to n upon n factorial. Okay, what should I do next? Can I do something here?
You can take t raised to n upon n factorial outside.
Exactly right. So I can take my t raised to n upon n factorial outside, and what I will be left with is just expectation of x raised to n. Can you all see something happening here? What's happening here? Anyone? So what I get here as coefficient is e raised to xn, right? And what is that? It is my nth moment, right? So this right here is my nth moment. So you see how in my MGF I have captured all the moments, because I'm going from, my value of n goes from 0 till infinite. So I have expectation of 1, I have expectation of x, I have expectation of x square, I have expectation of x cube as well, right? So this is what happens. I know that this is the coefficient. Basically, expectation of x raised to n is the coefficient of t raised to n upon n factorial, right? And again, if you must have studied a concept, so when the way we have expanded here, it's called Taylor series. And what happens if you evaluate a Taylor series at 0? It is known as Maclaurin series, and then you can easily see that, you know, this m. So the m that I was looking at, when raised to the power n and evaluated at 0, gives me expectation of x raised to n. And this is how, so when I'm talking about here, I'm not actually raising this to the nth power, but I'm taking the nth derivative of the MGF. And I think this is what Weber meant when he said that the calculation of MGF makes it easier for us to figure out the moments of any distribution, right? Because for variance, we have a formula which is the expectation of x square minus the expectation of x the whole square. And for skewness, it's a very long formula. And for kurtosis, we don't even know. So exactly, what you can do is you can just figure out the MGF and derivate it as many times and evaluate it at 0 to get the particular moment that you want. Does this make sense? Again, so the second property that I can say any MGF has is that it is unique to a particular distribution. So if I give you a MGF, so my MGF is always unique for a particular distribution. So let's say if I give you some random variable x and I give you another random variable y, and I say that they have the same MGF, what would it imply? It will imply that they have the same distribution as well. So again, this is very difficult to prove, and we don't have to need to know the proof. We just are happy with knowing the fact that this holds true for all the cases that at least we are concerned with. All right. And again, the next property that we have is again something that we can use. So let's say if I say that my x has the MGF mx and my y has the MGF and y. So again, I'm just ignoring this t that you have here. Doesn't mean if I'm not writing, it's not there. I'm just ignoring it. My slope notation, and I say that the x and y, these two random variables, are independent of each other. Okay, so now if I have to figure out the distribution of x plus y, what can I do? I want the distribution of x plus y. So I know the distribution of x, I know the distribution of y because I know that MGFs, and I know that MGFs are unique to each distribution. So I know the distribution of x, I know the distribution of y, but now I want to figure out the distribution of x plus y.
Multiply
What
them.
is it? Multiply what?
MXT and MYT.
Exactly right. So what I will do is, and what will I get if I multiply MXT and MYT? What should I write here?
Say suppose x plus y is equal to z, then it will give us mzt.
Yeah, exactly right. So I'm figuring out my MGF for x plus y here. And you will get some answer here. And once you know the MGF of x plus y, again using the fact that this MGF are unique for each distribution, you can determine the distribution of x plus y. Is this clear to everyone? Is this making sense? Am I going too slow or too fast? Please let me know, okay? No comments as yet? Okay, so I'm assuming that you guys are understanding what I'm saying and you guys are happy with the speed at which I'm at least teaching. So if you have any problem or if I'm going too fast or too slow, just please let me know, okay? Yeah. So again, so this was about MGF and we will see how to calculate the MGFs for distributions. And the only distribution which we have yet seen, which is relevant to our chapter, is the exponential distribution. The next distribution, which is a generalized version of the exponential distribution, is, can anyone guess? What is it? It starts from G.
Gamma.
Gamma, right? I really like gamma. Not distribution, but gamma function. Does anyone know what gamma function is? What is a gamma function?
The formula.
Yeah, I mean, it's, yeah, so it's right there in your formula booklet as well. But again, let me just write the PDF for the gamma distribution. So again, here we have two parameters. One will be lambda and the other will be alpha. So, and both of them, which we assume, are greater than 0. So I have alpha here. All right. Okay. And again, if I take my random variables to be x, I can write the PDF of my gamma distribution as something like this. So even I don't remember this, I'm just copying this from the book. X raised to alpha minus 1 times e raised to minus lambda x. Again, this holds true only for x greater than 0. And if this is the case, we say that my x follows gamma distribution with the variables alpha and lambda. All right. So if you can see, how do we have the exponential distribution embedded in this gamma distribution is if you put this alpha as 1, what you will get is 1 minus 1, 0. So this x cancels out. Gamma 1 is what? Does anyone know what is gamma 1?
1.
And why? Why do you think gamma 1 is 1 and not 0?
Because 1 minus 1 factorial is 0 factorial, and 0 factorial is 1.
Okay, so why is 0 factorial 1? Okay, take this as a homework. I don't want to reveal it to you guys. Maybe search it on the internet, but don't search directly, why is 0 factorial 1? Maybe search what does a factorial mean? And try to figure out what is 5 factorial, why is it 120, what is 4 factorial, what is 2 factorial, what is 1 factorial, and then come to, what can 0 factorial be and why is it 1? Like, it makes all logical sense for a 0 factorial to be 1, but take it as a homework and I'll maybe
Zero
ask it to
factorial.
Yeah.
0 factorial would be 0, then all of the factorials would be 0.
No, it's not like that. It's not like that. No,
Okay.
that is not the reason actually. That is not the logical reason that I'm looking for, but that is a true statement. I mean, I don't know exactly, but yeah, I mean, no, that is not, no. I wouldn't say that's correct.
Okay.
Because see, what is 1 factorial? It's 1, just 1, right? So let me just write it. If I'm talking about 2 factorial, what is this? This is 2 times 1, right? If I'm talking about 3 factorial, this is 3 times 2 times 1, all right? So if I'm talking about 1 factorial, it will just be 1. And if I'm talking about 0 factorial, shouldn't this be 0? Like, from what you guys are saying, it should be 0, right? At least there should be nothing, if not 0. And for us, we denote nothing by 0. So what's happening? Why is this 1? So again, I think what will help is, if you guys must have studied, those boxes full of problems. They ask you that you have these 3 boxes and I give you 3 letters like A, B, C. So how many words, how many different words, which can be meaningless as well, can you make from these 3 letters? So what you have is, that you have to make a 3-letter word and you have 3 choices. So you know that for this first box, you have 3 choices, right? 3. And again, if I'm telling you that I don't want any repetition, so if you take 1 letter out of these 3 here already, then you will be left with only 2 letters. So I'm assuming that the letter you take here is C. So you'll be left only with the 2 letters. So you will have 2 choices here and you will only be left with 1 choice here. So this is what the 3 factorial in a way means. So now think of what is 0 factorial, and yeah, just tell me why is it 1. So you can think about it and we can go ahead with what we were doing. So again, gamma function, let me write the gamma function. So people make this, 10 most beautiful destinations to visit in the world, 10 most beautiful theorems in mathematics, but there is no list of 10 most helpful or beautiful functions in mathematics. And I think if there was a list, gamma function would top it always. Not only according to me, according to like general consensus in the mathematical community. So if I have to write my gamma alpha here, it will be an integration from 0 to infinity, x raised to alpha, e raised to minus x, dx upon x. So again, if I may ask you guys, so actually what happened, the person who came up with gamma distribution didn't come up with the distribution first. So we knew the gamma function prior to us knowing the gamma distribution. And what this guy did was just terribly smart. And can you guys see the relation there is between this gamma function and the PDF of the gamma distribution that I have written on the board? Are there any similarities? What were the discrepancies? And basically, can you guys see something happening over there? Anyone? So what is the foremost thing that we need for any function? Okay, so I say that, this is a PDF, but at the end it is a function, right? It has that F at the end. So it is a probability density function. So what makes a function a PDF? Anyone? What is the necessity condition that any PDF must have? Oh, this should be a very easy question.
It should lie between 0 and 1.
It should lie between 0 and 1. That's good. And
it should be greater than or equal to 0.
So when you said it should lie between 0 and 1, you meant its output should always be between 0 and 1 because it is representing a probability, right? Perfect. And what is the next condition?
X should be a random variable.
Yeah, that's good too, but that is like not what I'm looking for. Come on, come up with other things. What do we know about this guy named PDF?
Sum of all probabilities is 1.
Exactly what I was looking for. So we know that the sum of all the probabilities in a PDF, which are just sum of all the which is just sum of the function that we're looking at for all the different values that X can take, should be 1 always, right? Irrespective of any PDF that we're looking at. So now, if I give you guys this gamma function, and if I tell you to come up with a distribution, can you do that? So, okay, let me maybe make it a bit easier. So when I'm saying, when Vaibhav said that the integration of f of x should be 1, right? So let's say if I give you something like this, that I don't know why is this pen tricking me today. So if I give you something like this, that my 3x is equal to 4. Okay, but I don't want this 4 to be 4. I want this right hand side to be 1. So what should I do here? What should I do here to make this right hand side as 1?
X should be the inverse of 3, so 1 by 3.
What?
Divide LHS also by 4.
Yeah, Vaibhav, you're on the right track. Did you say 4? So, see, if I want 1 here, what I have to do is I have to divide both RHS and LHS by 4. So what I will have here is 3x upon 4. And here I will have 4 upon 4, which is just 1. So what I did was, whatever was on the RHS, I divided by that number, both the sides, which will render the equation to be equal. So now I have this, 3x upon 4 is 1. So if I have the integration of some function which is equal to this, and I want this integration of some function to be just 1, what should I do? I should just take this down here, right? So what I will do is I'll have integration from 0 to infinity, and I have x raised to alpha here, But remember, I have this 1x down here as well. So I can write it as x raised to alpha minus 1, right? And I will have my e raised to minus x here as usual. And I will have upon gamma alpha dx. Does this make sense? Because I'm integrating, I will have integration of f of x dx, just for the completeness, right? So this is how you come up with a gamma distribution. But you don't see this lambda here, right? So again, this is just my gamma distribution with lambda as 1 and alpha. And for flexibility reasons, you can add lambda here. So instead of this 1, you make it some number and you get lambda raised to alpha and lambda here. So this is just something that you need not know, but something to think about and something that you can, it's better to know. So again, what's important to us here, let us focus. So what we have here is a gamma distribution, and I'm not deriving this, and maybe you guys can, and I'm assuming you guys know how to derive this. So my expectation of x will be alpha upon lambda, and my variance of x, where my x follows gamma, will be alpha upon lambda square. All right, and this we have already established. Oh, and again, we do have this interesting thing, right? So what is gamma of half? What is gamma of half?
Under root pi.
Under root pi, right? Isn't this interesting? So I think this is just what we need to know. I could go on and on about, just explaining about gamma function, but I'm already looking at the time and it's 4:30 already. But yeah, okay. So I think that's good. We didn't cover a lot today, but I guess, so let me just ask you guys this question, do you enjoy the way I'm teaching, or is it too much, or is it like, how do you guys feel about the teaching? Because if it's annoying, let me know. If it's too much, do let me know. If it's good, do let me know. So yeah, I just don't want you all to, be lost in the lecture and then try to just, not be able to understand anything. So maybe we will go slow in the start, but trust me, if once you get hang of this concept, you will never forget this for the rest of your life, and you will always, be comfortable with handling any complex sum that is given to you, not only in exam, but in the practical scenario where you will be giving computer the orders. So yeah, I guess this was all about the gamma distribution, and I should share the PDF. I will share the PDF, and that is when I'll start giving you guys homework as well. Okay, so maybe for today, so I'll actually share the PDF of the book. So I'm assuming that you all don't have that already. So I'll share it in the WhatsApp group, and I think it's just easier for anyone who's taking the exam to get hold of that. And yeah, so again, so let us revise what did we do today, and it's only easier for us. And if you all want to stay, we can also, I guess, do the graph of the Memoryless that I was talking about. Yeah. So again, who would like to explain what we studied on this slide? Come on, I need volunteers, and I will keep note of whoever is explaining. If it were an offline class, you would have gotten, a chocolate or something from my side to answer each correct question and to summarize the whole lecture. But anyways, I can't give you anything online, but I'll give you online brownie points if you can explain what we studied in this slide. Anyone? Come on, fast. Within a line. I don't want a paragraph, just one line. That's it. Nothing much.
The relation between Poisson and exponential distribution.
Yeah, that's it, right? So we studied the relation between Poisson and exponential distribution. And what did we see here? Again, the same thing, right? And then what did we see here?
Memoryless property and the assumptions for it.
So what is the memoryless property, if we can summarize it again for us?
It is the property where the events are independent. I mean, the prior event is not dependent on the next event.
So the future event is not dependent on the prior event, right? Perfect. And there are some assumptions that we need to keep in mind. Perfect. And next we saw just some questions. And what did we study here? It's just some random stuff. Again, the same memoryless property. And here, what did we study?
Moment generating functions.
Right. And what is the main property of MGF?
That it is unique to a distribution.
Right. That it is unique to a distribution, right? And its formula is expectation of e raised to tx. Very important. And what did we study here? Just the gamma distribution, right? And the gamma function and the relation between them and blah, blah, blah. So, okay. Memoryless. I'm actually very much interested to show you guys this, actually. So, let me maybe erase this as well. Or maybe we can keep it. So what I will do at the end is, once we have all of this, so this will be my first flip chart for the first chapter, and I will save it as a PDF, and I will share that PDF with you guys at the end of the lecture, right? So you did not take the notes if you just want to, keep this with you, because I'll be sharing the PDF at the end, so you can just sit and watch and be in the lecture. But if you're interested in taking notes simultaneously, you can do that as well. So that's good, but I would encourage more of thinking than writing. But I know some people can think while they write as well. So yeah, you can do both. So that's amazing. Okay, let's come back to the memoryless property. And I think for this, I think it's easier to not look at the car example, but let us say that, you're traveling from A point to B point. And what you're worried about is the petrol tank of your car or the diesel, whatever. So let me draw. Here I have X. Okay. Okay. So what I'm looking at is an exponential distribution. So I should draw one. So let us say I have something like this here. Okay. And it starts at lambda. So this is how I'm just defining it. It did not be this case always, but this is just how I'm defining it. So when you are here, this graph represents a new petrol tank. Basically a petrol tank which has been just filled up 100%. Okay. So now what I do is, I have passed some time. So my car has driven from A to some point C, which is in between A and B. And let me define this point as C here. Okay. So what will happen is, right up until here. So now if I have to figure out, the remaining petrol, and if I look at the PDF here, what I get is just this remaining graph right here. So I know that if this whole graph, the area under this curve sums up to 1, then the area which is only left to the C point that I'm talking about will not exactly be 1, right? And if I want this to be a PDF, what I do is I rescale it. So I'll carry this up forward And this drawing is a bit tricky. So, and you rescale it. And you draw this curve again. So, what happens is, now this is my rescaled version. And here, this curve represents the trajectory of my used tank. So I've already used the petrol in the tank up until point C. So this is the trajectory of my used tank. Okay. And when I'm saying that this exponential distribution has memoryless property, what I mean is that this green graph and this pink graph, they both are equivalent in terms of the remaining time for the petrol to be emptied completely. And when I'm saying that, that what's happened here previously does not in any way define what's going to happen in the future, what that allows is, if you pick up this line, if you pick up this curve here, pink curve, and you just substitute, just place it, let's say, over this green line, it will overlap each other. So maybe my drawing is not as good as it should be, but the rescaling is done in a way that this overlaps the green one exactly, and that this area, so this area that you have will also sum up to 1. And this is just how you can visualize the memoryless property. And this is what's actually happening. So when I'm saying that, I have moved forward, let's say if this was my S, and I'm saying that I have moved T steps forward, so this would be my T. So I'm figuring out something that will happen after S plus T. So after basically C. So it will be all of these. And this is the probability. But here I'm looking at, the time for it to be completely emptied, the time for the petrol tank to be completely emptied, and the time for me to fill it again. So this is the exponential decay that we usually talk about. Did this make sense to you guys? Okay, yeah. Just unmute yourself and say, okay. It's very difficult for me to see in the chat box, but yeah. So I guess that's all we have for today. And in the next class, we will study some other distributions like Pareto, Weibull, and Burr, log normal. Yeah, so normal is what you cannot use, but we'll see log normal is something that we can use. So again, remember the homework that I have given to you guys, and I'll pass on the PDF of the book as well for you all to, solve the questions. I mean, not many questions are which you can solve right now, but yeah, a couple of them you can do. So I guess that's all from today. That's all from my side, at least for today. Does anyone have any question in regards to today's lecture, previous lectures, or anything that we have studied as yet? Anyone? Oh, and also, so tomorrow is Dashera. And what time do you guys think? Should I keep a lecture tomorrow, or is it better to not keep a lecture tomorrow and just keep it day after?
Ma'am, can we have classes on weekdays?
Yes, ma'am. Even I am not that comfortable for weekends. And
Yes, ma'am. Weekday would be better for me.
Oh, perfect. So I think let's keep it on weekday. And okay, let me jot this down. So what days do you guys feel more comfortable, for lectures? I mean, the days when you don't have much work from either college or your work.
Ma'am, any day is fine, but I think this time is comfortable for me. Same 2
Okay, so we'll keep one.
Evening
Okay,
will be more comfortable because it's like we have college in the morning and then immediately this, so it becomes.
I have colleges in the afternoon.
this time is comfortable for me on any weekday.
Okay, so Can we keep classes at I see. So can we keep classes in the late night? How about 7 o'clock, like 7 to 9? Is it fine with everyone, 7 to 9?
That would be a little late, obviously. Like if you
Yes,
could
ma'am.
keep 4 to 6 or maybe 5 to 7, then that would be fine.
And 5
So
to 7.
actually,
5 to 7. Yeah, 5 to 7.
5 to 7 is fine.
I would have kept lectures around that, but I am a Gen, so we eat dinner before the sun sets, and sun sets usually around 6. So I have to make my dinner and I have to eat it as well. So that would be difficult for me. So
Ma'am, how about 6 to 8?
I'll have to run from my dinner. So wait, can we keep it from 6:30 till 8:30? How about that?
Yes, ma'am.
That would
Yes,
be
ma'am.
fine.
Okay, ma'am.
Perfect. We have reached a consensus. So okay, we can keep another lecture on Monday then. Is Monday cool?
Yes.
Yes, ma'am.
Okay. Okay, so I'll update in the group as well. The next lecture would be on Monday from 6:30 to 8:30.
Ma'am, when will we be having the classes on weekdays? Like which days?
Oh, so Monday and Saturday, is that fine?
So, ma'am, Saturday we can have the class at this time only, like 2:30 to 4:30, and then maybe Monday once in the during the week we can have
Yeah.
6:30 to 8:30.
Yeah, so I guess for now,
Ma'am, it
I
would be
have
great if
college
both the
lectures.
lectures we have on weekdays instead of weekends.
okay.
Yes,
Okay,
ma'am.
so let us keep it on Monday, and the next day could be maybe right after it, or if you guys want a break between the lectures, then, but I want you all to,
Thursday.
at least study some substantial amount for like 2 days and then go through it over the week. So maybe we
So
can keep a
Monday.
lecture on Tuesday. Yeah. Monday and Tuesday sounds good. So maybe let us keep a lecture on Monday as well as Tuesday. I'll update this on Monday. Yeah. So I think I'll update in the group that we'll have a lecture on Monday. Okay then. And do let me know if there. Yes.
So you'd said that initially you'd be taking lesser lectures and then later on you'll be taking more lectures, right? Like if you feel. So,
Yeah.
yeah. So instead of that, like, because I feel that many of us will be having our exams in December. So could you just like, like right now till the time October is finishing and even November, I think it's okay if you take more lectures that time, and then later on when we have our assignments and all, we really need to spare time for that, and even during the exams.
Yeah, I think that's okay with me. How about everyone else?
Fine.
So,
Yeah.
yeah. So what we can do is we can take 3 lectures in a week.
Yes, ma'am.
Yeah. So we can have a Monday, a Tuesday, and not Wednesday. I would say when you guys
Monday, Wednesday, Friday.
Okay, that works well. So Monday, Tuesday break, and then we'll have Wednesday and Friday. Okay, cool. So Monday, Wednesday, and Friday. Okay, perfect. So this will start from the next week onwards. And I guess it's only nicer for you guys, to be in loop always. Otherwise, you'll forget about actuarial science and just go and, I mean, that's not likely to happen. But yeah, okay, perfect. So I guess that's it for today. And it was lovely to have you all. Happy Dashera in advance. I don't know how many of you celebrate and how are we going to celebrate this time. But yeah.
Ma'am, every day you have dinner before sunset.
Yeah. So for today, actually, I had to, prepare for my dinner before. So I prepared for my dinner in the afternoon itself so that, I knew that I would extend the class anyways beyond my times, beyond my scheduled time. So yeah, I prepared my dinner. I mean, I made preparations for my dinner. So I just have to go home now and just cook it. Yeah, that's it. Anything else? Okay, then I'll end the meeting and enjoy the rest of your weekend, I would say.
Thank you, ma'am.
Thank you, everyone.